Here's a problem that we know we can't use SOHCAHTOA for because it's not a right triangle. We might try to use then the law of cosines to solve for this unknown side over here, x. This angle is 111 degrees, this is 33 degrees, the length of this side is 50. I've told you that probably the easiest way to properly apply the law of cosines is to identify the angle first, because there's only one angle in the formula, but there's two given angles here, and we certainly could find the third one if we wanted to. Which one should we use in this case? Well, maybe we need to guess. Since we're interested in this side, which is across from the 33-degree angle, maybe we would guess that this capital C should be 33 degrees, and therefore that the side across from that would be the x squared is equal to, then the a and the b are the other two sides, 50 for the a. Oh, now we run into a problem because we don't know what this side is. B squared minus 2 times 50 times b times the cosine of 33 degrees. We have two variables in this equation. We can't solve this for x and get a numerical answer, so that didn't work. Maybe we should have chosen the 111 degree angle instead. Cosine of 111 degrees, and then the side across from that would be the x. 50 squared is equal to, and then the other two sides are the x, and then, oh, we're in that same problem again. We have two variables in this equation, and even if I finish it out, I can't solve this equation for x and get a numerical answer unless I know the value of this side here. So the law of cosines is not working for us here, and what will work for us instead is this other law, which again I'm not going to take the time to prove. It's called the law of sines, and it can be written in one of two ways. The sine of angle A over lowercase a, which is the side across from that angle, is equal to the sine of angle B over lowercase b, which is equal to the sine of angle C over lowercase c. Now, this equation is true. This equation is true. Take this out of the middle and you have another equation is true. All three of these ratios are equal to each other, but I've never seen a problem where you needed all three of them to get one answer. If you want to find one missing side or one missing angle to a triangle, you really only need two ratios at a time. I wouldn't try to work with all three at a time. You might need to use the law of sines twice to solve a problem, but anytime you use the law of sines, you're really just using two ratios at a time. This is for all triangles. It will even work for right triangles, but I would still use SOHCAHTOA for right triangles. SOHCAHTOA is still the easiest thing available for right triangles. If it's not a right triangle, you're going to have to use the law of cosines we learned the day before, or the law of sines that we're learning right now. Here's another way to write the law of sines. You could turn all of these ratios upside down. A over sine of angle A equals B over sine of angle B equals C over sine of angle C. Mostly, you'll only ever see it this way in books or online, but this way is just as effective. It really doesn't matter which way you start with the law or the formula. For me, I like to use this version of the law if what I'm trying to solve for is an angle measure, because the angle measures are in the numerator. And I like to use this version of the law if I'm solving for a side length, because this version has the side lengths in the numerator. I'm just going to zoom in on that law a little bit again there, because I don't know how clear this video is going to be, but that's the law. Okay. Sine of angle A over A equals sine of capital B over B equals sine of capital C over C, or you could flip all those ratios upside down. Okay. This law will help us find this missing side in this problem. To use the law of sines, you need to pair up sides and angles that are across from each other. This side is across from this angle, and conveniently, we have another side across from another angle. So if we have two pairs like that, we can use the law of sines to solve for the one missing part. Again, since this is a side length, I'm going to use the version of the law that has side lengths in the numerators. So I'm going to put x over the sine of the angle that it is across from is equal to this side, 50, over the sine of the angle that it is across from, 111 degrees. Okay. As with the law of cosines, the A and the B and the C can be any of the sides in the triangle. The C does not have to be the largest side. Okay. What is important is that capital A angle is across from little a side, and so on with the B's and C's. So to solve this problem for x then, all that we need to do algebraically is multiply both sides by the sine of 33 degrees. And that will cancel out the division by the sine of 33 degrees over there. Pick up your calculator, x equals all of that. You can punch that all in your calculator just exactly the way it is. And assuming your calculator is in degree mode, okay, and it hasn't been changed on you while you weren't looking or paying attention, you should get an answer for x of approximately 29.2. Occasionally, some students, after they've learned the law of sines and the law of cosines, will get stuck on a problem or just get a little trouble and want to know, Mr. Nortello, how do we know when to use the law of cosines and when to use the law of sines? I don't know which law I'm supposed to use. And there's a couple answers I could give to that question, but the one that I'm going to give is you don't need to know. Try one. We tried the law of cosines with this problem. It didn't work. And it doesn't take that long to find out that it doesn't work. If you try one law and you try to apply it and it doesn't seem to be working, you probably will not have lost more than 15 or 30 seconds. And then tell yourself, I probably got to go back and use the other law and try the other one. Now, once you've done a lot of problems, you will probably get pretty quick at recognizing which law is going to be helpful to you. There are rules that I could give you for how to know when to use which law and when to use the other law, but I don't think the rules are really all that helpful. I think that's a lot more memorization than you really need to do. I think you'll get just as good at knowing which law to use just by doing plenty of problems, and maybe thinking about it a little bit as you go. Let's do another problem using the law of sines, this time to solve for a missing angle measure instead of a side length. I'm going to put that missing angle measure down there, and I'll give an angle measure over here of 30 degrees, and we'll put a 25 along that side, and we'll put a 20 along that side. Once again, I have a side and an angle that are across from each other, and I have another side and an angle that are across from each other. Okay? That's a pretty good clue that the law of sines will be useful to us here when you have two pairs of angle sides or angles and sides that are across from each other. I'm going to put the x in the numerator. I always like to put the x in the numerator, but this x is an angle, and so I've got to write sine of x over the side across from it, 25, is equal to the sine of 30 degrees over the side across from that, 20. This takes just a little bit more algebra to solve than the previous problem. First thing we're going to do is multiply both sides by 25. That will cancel out the 25s there. If you put all this in your calculator, it will give you a decimal value of 0.625. But that is the sine of x. And now we have one thing remaining to do here, which you probably know how to do, and that is to take the sine inverse of both sides of this equation. That will effectively undo the sine on the left, leaving the x standing alone. Put that into your calculator, and you will get approximately 38.7 degrees. Okay. Hold on, wait a minute. 38.7 degrees. Look at that picture. Does that look like a 38.7 degree angle to you? Maybe it's a bad picture. Well, if this is 25 and this is 20, I mean, does that seem reasonable that if this is 25 units long, that's 20 units long? I think that should seem reasonable. This segment looks to be a little bit shorter than that one. Does this angle appear to be a 30-degree angle? Well, I would say so. Why is this picture so far off from this angle measure here? Okay. Well, we got to go back to the unit circle to understand what's going on here and to know whether or not this is actually the correct answer. Okay. Let's go back to the equation we had just before we got the answer to this question. Sine of x is equal to 0.625. Okay. We go back and revisit the unit circle. And I ask this question. Where is the sine of x equal to, let's make it exactly 0.5? Well, there's two places. Right here at 30 degrees, but also right here at 150 degrees. The sine of 30 is the y-coordinate here, 1/2. The sine of 150 is the y-coordinate here, also positive 1/2. Okay. So maybe the answer to that question we were working on really isn't the acute angle. Maybe it's the obtuse angle instead, where the sine is equal to that same value. We were dealing with this. Sine of x is equal to 0.625. That's a y-coordinate, which is slightly more than 0.5. And the angle measure we got was about 38.7 degrees. That's where the y-coordinate is 0.625. But there's another place on the circle where the y-coordinate would be 0.625. It would be over here, a little bit above the 150. Now, if that is 38.7 degrees up from 0, this point over here would be 38.7 degrees going backwards from 180. So we would find that angle measure by subtracting the answer that the calculator gave us from 180 to get 141.3 degrees. And if we go back to the problem we were working on, I'm sure that looks like a much more reasonable answer. Here's the diagram. You tell me, 38.7 or 141.3? 141.3 looks a lot more reasonable. Oh, but here's another catch. I could redraw this diagram, and keeping all of this information the same, the diagram would look quite different, but all the values would still look reasonable. Let me show you what I mean. Let's start out with a 25 degree or 25 unit length on the left, just like that one. Let's create what looks like about a 30-degree angle down there. Now I need a 20 unit length over here on the right side, except I'm going to draw that 20 over here and then extend this 30-degree angle to meet that side. Wouldn't you agree this segment still looks a little bit shorter than that one? If this one's 25, that could be 20. Wouldn't you agree that this angle still seems to be roughly 30 degrees? And then if I put the x over there, I have a diagram whose information is perfectly consistent with this diagram here. But now that angle looks like it might really be 38.7 degrees. So what's the answer? The answer is, in this case, there are two solutions. There are two possible values for x. 180 minus the 38.7 equals 141.2 degrees. Two possible solutions. I'm sorry, that went off camera there. 38.7 or 141.2. So, here's something that you have to know about using the law of sines. When using the law of sines to find angles, not segments, but angles, okay, you must look for two possible answers. Okay. Now I'm underlining the word possible because sometimes the second answer that we find won't make any sense. You can always find a second answer, and the way you find it is always by subtracting the first answer you get from 180 degrees. The calculator will only ever give you an acute angle answer. You have to consider the possibility that there is an obtuse angle measure. But then you even have to go beyond that. You might have to throw out that obtuse angle measure and tell me in the end, in the final analysis, no, there really is only one good answer to this question. I'm going to show you how you can tell. Okay? But you have to look for two possible answers, and then after finding the second, you might have to cross it out. Okay? It might not really be a legitimate answer. And how are you going to know? All right. Well, let's do another problem. So, let's make this angle up here look like about 105 degrees. Let's make this side 40. Let's make this side 50. So this side clearly longer than that side over there. Not by a whole lot. Okay, but it should look to be a little bit longer. Let's put an X in there. Okay. Let's say we're looking for that X. We have a side and an angle across from each other, a side and an angle across from each other. So the law of sines is probably going to help us here. Sine of the angle we're looking for, x, over 40, the side it is across from, is equal to the sine of 105 degrees over 50. Okay. Let's multiply both sides by 40. Cancel that out. Sine of x is equal to approximately 0.7727. We take the sine inverse of both sides. That cancels out sine, leaves the x standing. X is approximately 50.6 degrees. Okay. Or, now we got to consider the possibility that there is an obtuse angle measure. Okay. 180 minus 50.6 is equal to 129.4 degrees. Is that a possible answer? I guarantee you the acute angle answer is a good answer if you've done your work correctly. What about the obtuse angle, 129.4? Go back to the diagram. We already have 105 degrees worth of angles in this triangle. We don't have room for another angle that's 129.4. That would be way over 180, and we would not even have included this angle over here. So this 129.4 doesn't fit. Okay? You have to go back to the diagram and ask yourself, does that obtuse angle also fit in the original triangle? Now, if you look at this original diagram and recognize there's already one obtuse angle in here. No way is there going to be room for another obtuse angle. Then you kind of don't even have to go looking for that obtuse angle solution. Okay? But do the work thoroughly. Okay? Don't jump to the false conclusion, for instance, that just because, for instance, if we're doing a problem with an acute angle in it, like this first one, that, oh, then there's guaranteed there's going to be room for an acute angle or an obtuse angle over here. You can't say to yourself, I know this diagram is going to have two solutions because the starting angle is acute. You can't say that. There might still only be one solution in a problem like this. Find the obtuse angle measure, decide if it fits, and if it doesn't, throw it out. Okay. In honesty, though, in all honesty, you are safe in recognizing that if you're starting with an obtuse angle, there can only be one solution to the size of this angle, and another obtuse angle is definitely not going to fit. Okay? So that is pretty much the law of sines. And again, you don't have to become really quick and really great about choosing which law do you need to solve your homework problems, the law of sines or the law of cosines. You can just try one, and if it doesn't work, go to the other one. On tonight's homework, let's see, homework. Here was Thursday night's homework, where I ordered you to use the law of cosines to solve these problems, and then I ordered you to use SOHCAHTOA on these, because it's really the easiest way to go. Here's tonight's homework, where I am ordering you to use the law of sines to solve for all the missing parts here. When you get down to set B, I'm asking you to solve for the variables. I'm not telling you which law to use. Since there are no right angles here, you cannot use SOHCAHTOA. You're going to have to use the law of sines or the law of cosines, but I'm not telling you which one. So you'll get some practice here making a decision about which law to use. If you're not really sure, then just jump in and use one. It'll work or it won't, and if it doesn't work, you'll find out pretty quickly. Then just back up and start over with the other one. With this set of problems here, I'm saying solve for all the missing sides and angles in these triangles. Well, you can only solve for one missing thing at a time. Okay? This triangle has 3 missing angles in it. Pick an angle, solve for it. Then pick another angle, solve for that. You may need to use the law of sines twice in this problem. You may need to use the law of cosines twice. Maybe you're going to use the law of cosines once and then switch to the law of sines to find another angle. I'm not giving you any hints. Find your way around to a solution. In this diagram over here, there's 2 missing angles and 1 missing side. I'm not telling you what to find first. You're going to have to think about that. Maybe you're going to try to figure out a way to find this missing angle down here and see if the law of sines will help you. And if it doesn't, maybe you'll try the law of cosines. And if that doesn't work either, maybe you picked the wrong thing to try to solve for first. Maybe you'll have to find this missing side first. So there's quite a bit of decision making that you're going to have to make in tonight's homework. These problems here, numbers 10 and 18 in, number 18 in section 9.10 of the book. Don't overlook that problem also. Here's all of the answers, but none of the work. I may get around to posting worked out solutions. Check my webpage as always. Email me with any questions, and come prepared for the quiz on Monday. We'll see you then.